Todos. Este día tenemos el gran privilegio de contar con la presencia del doctor Issa Nesnas, quien trabaja en la NASA y que tiene la intención de presentarles primero esta ponencia sobre robótica y autonomía en el espacio. Es la primera conferencia, ahorita a las 12, y después vamos a tener una segunda conferencia a las 5 de la tarde sobre oportunidades de interacción con la NASA, a la cual también todos ustedes están cordialmente invitados. Y quiero comentarles, el doctor Issa Nesnas es el tecnólogo principal en la división de sistemas autónomos del Laboratorio de Propulsión a Chorro, donde trabajó durante más de 25 años, después de varios años previamente en la industria de la robótica, específicamente en robótica industrial. Actualmente él es el director asociado del Centro de Tecnologías y Sistemas Autónomos de Caltech, de este tecnológico de California, y líder en este laboratorio de propulsión de jets, JPL por las siglas en inglés, en el equipo de liderazgo de capacidad para sistemas autónomos de la NASA. En JPL dirigió los grupos de movilidad robótica y sistemas de software de robótica a lo largo de 13 años. Sus investigaciones incluyeron arquitecturas para sistemas autónomos, navegación y manipulación basada en la percepción, así como movilidad en terrenos extremos y en microgravedad. Ha desempeñado múltiples funciones en 3 misiones de Rover de JPL. Ha recibido el premio Magallanes, que es el más alto reconocimiento de JPL para un científico individual o un logro técnico en su trabajo, en este caso movilidad extrema en terrenos. Él es ingeniero eléctrico por el Colegio Manhattan, lo obtuvo en 1991, y una maestría y doctorado en el área de robótica del Departamento de Ingeniería Mecánica y Aeroespacial por parte de la Universidad de Notre Dame en los años 1993 y 1995. De verdad, como les decía, es un privilegio contar con su presencia. La conferencia va a ser en inglés, pero le hemos pedido que hable muy despacio y que hable muy claramente para que todos, incluyéndome yo, podamos entender lo que nos quiere transmitir. Quiero decirles que, su presencia aquí, es en parte, por supuesto, al trabajo que todos estamos haciendo y que esperamos que ustedes, muchachos, con su esfuerzo en sus carreras, sigan haciendo las cosas bien como lo están haciendo ahorita y, si es posible, lo hagan mejor para que eventualmente puedan ustedes aprovechar las oportunidades como esta de tener un intercambio, una comunicación con el doctor Nesnas. Y también, ¿por qué no? Eventualmente, a lo mejor, trabajar para la NASA o algún organismo tan importante como este. Entonces, les voy a pedir nada más, por favor, que durante la presentación vayan pensando en esas preguntas, en esas inquietudes. Y, por favor, el doctor Nesnas está de veras muy gustoso también de contestar sus preguntas. Y yo espero que aprovechen ustedes esta oportunidad de tener a una personalidad como él aquí el día de hoy, y lo pregunten y lo cuestionen, así que le saquen toda la sopa para que les sirva la información que les pueda transmitir. Sin más, les dejo la presencia del doctor Issa Nesnas con ustedes. Doctor Nesnas, please.
Muchas gracias, Emilio. So it's great to be here. Everybody hear me okay? So this is going to be in English, but I do want to say a few words, and please bear with me here. Es un gran placer estar aquí en San Luis Potosí para visitar su universidad y compartir con usted el trabajo que estamos haciendo para la NASA en la exploración espacial. Estoy muy agradecido por mi colega y amigo, el profesor Emilio Jorge González Galván, por invitación. Thank you again, Emilio. Hello. It's a great, great pleasure to be here. Thank you all for coming. And this is your lunch hour, so I really appreciate that you all made it here. My goal today is to tell you a little bit about what we do for space exploration. First of all, I come from a place called JPL, which stands for Jet Propulsion Lab. By raise of hands, how many people heard of Jet Propulsion Lab? Okay. So let me tell you a little bit about JPL. So this is the campus where I work. I do work in this building here. And JPL is in Pasadena, California. And it was founded in 1930. Now, if you remember, NASA was formed in 1958. So this actually was formed before NASA was formed. JPL is what's called a federally funded research and development center. It is part of Caltech, California Institute of Technology. And it is a federal facility that develops technology and flight systems for NASA. Now, JPL is responsible for many firsts in space. So the first US satellite that was developed was actually developed at JPL in 1958. That was in response to the Soviet Sputnik, which was the first satellite, and the US developed its own in that year. But later on, there were two missions. Have people heard of Voyager 1 and 2? Raise a hand. Okay, so some of you did. So Voyager 1 and 2 actually were planetary missions. They actually flew by many of our planets. But now they're so far away, they're 24 billion kilometers from Earth. That's Voyager 1, and Voyager 2 is about 20 billion kilometers. So now they're actually exploring interstellar space. A lot of the pictures that you've seen early in the textbooks in science actually were pictures taken by Voyager. A more recent one in 2004 was a Cassini. Cassini was a mission that went to Saturn and explored Saturn and its moons. So if you go online and you want to look, there's a lot of detail now we know about the rings of Saturn. And that's actually from this mission called Cassini. And of course, people are familiar with the rovers? I'm going to talk a lot about the rovers today. Okay, excellent. So the rovers, so the first Mars rover was called Sojourner. It was in 1997. And then we also have the first rover that caches a sample, that collects a sample, and seals it. And the point is to be able to eventually return it to Earth. And that's done with the current rover on Mars. That's the latest rover we have called Perseverance. And people know what Perseverance also put on the surface? Helicopter. So we have actually a helicopter flying on Mars today. If I recall correctly, it's done either about 52 flights, if not 53 as we speak. So that's the first flight on another planet that happened. So these are some of the things that the place I work at has been developing. I've been there 26 years, and it's been a lot of fun. Okay. So let me take a step back and say, why do we explore space? And why we explore space and the planets. So the first thing is the big science questions we're trying to answer. The first question is the origin. How did the solar system form? The other question is, what worlds are out there besides our world? And what are the processes, the geological processes, how things work on other planets? And the other question, is there other life out there? Or are these planets conducive to having life on them, which is what we call habitable? Habitable means, do they have the right conditions? Do people know what you really need to have life on other planets? There's only one thing you need. Anybody? Water, right? People thought you need oxygen, but we discovered actually life on Earth that doesn't require oxygen. So water is key to finding life. So let me give you a few examples. So one of the things about origins is a mission concept called endurance. And actually, I did work on this mission concept. So this is the picture of the moon. And this is taken from a slightly weird angle. This is the South Pole. And this one here is called the South Pole Aitken Basin. Now, the color here, you can see the color chart is, what is the altitude of that? So this is a big depression on the moon. This happened, or it's believed to have happened, through a large impact, and that generated this. And by having a large impact in the solar system, what happens, it churns up the material from underneath. So if we want to look and understand how the interior of the moon is formed, one of the things we can do is go and collect a bunch of samples from this big basin. Now, how are we going to collect these samples? So you see the route here. It's from here. If we land here, we need to go all the way and collect samples along the route. This is the equivalent of driving maybe from San Luis Potosí to Mazatlan. That's kind of the distance we have to drive with the rover. But of course, nobody there to drive it, so the rover has to do that on its own. So this mission concept is to go in and drive 2,000 kilometers and to collect 12 samples and about 100 kilograms of samples. One of the things we need to do, because if you remember on the moon, the daytime is about, depending where you are, but roughly it's 14 hours, 14 Earth days, and at night is also 14 Earth days. So you have to be able to drive during the day and at night, so you can keep making progress, because we want to do this in 4 years. And then what you do is you collect the samples, bring them, and because we're going to fly and put astronauts on the South Pole, then the astronauts will come and actually pick up the samples and bring them back to Earth. And this is a concept, and this is an evolving concept, so it gives you a sense of what the rover looks like. It looks similar to the one we put on Mars, and it has these collections, the cache for the samples, and there's an arm that collects the sample and puts it here to bring to the astronauts to return. So let's look at another example. So another example of why we explore space is understanding worlds and processes. So this is a picture of Uranus, and one of the key things we want to understand, and actually Uranus, people don't know, it actually has rings. And one of the interesting things about Uranus is that the axis of rotation is tilted 90 degrees compared to all the other planets. So it's very intriguing. And there's a system of moons and rings around it. And we know very little about Uranus because we only know what we've seen from the Voyager imagery. So one of the key interests in the science community today is to go and explore this. And this will take many years. It may take 10 years and another maybe 6 years to get there. So it'll be like, you know, a long time from now. But that's one of the things that people are working on today. One of the things about space exploration, unlike what you can do on the internet, is you have to be patient, because the distances to go from one place to another is very, very, you know, it takes a long time. Sometimes it takes 13 years, 16 years to get to where you want to go. So you have to be very patient. So another place here is really exploring water and ice on Mars. So one thing I mentioned, what's really important for life is water. And for a long time, the strategy for exploring Mars was follow the water. So this is a picture of Mars, and this layer that you see here is made out of actually water ice. And this is at a pretty steep angle. And another interesting place that people think could be water, but sometimes they think it may not be water, is what's called the recurring slope linear. You can see this, there's animations where you see these lines here, and people thought, oh, this looks very much like flowing water, and they study it. But of course, liquid water on Mars is unstable. But for this to be stable, people think it could be extremely salty flows. Now, what you see here is some of these things are much harder to access than where we've been to on Mars. And I'll come back to these later on in my talk. Another thing is life and habitability. So have people heard about ocean worlds? Anybody? Okay, some people did. Okay. So we discovered a whole bunch of planetary bodies that are covered by huge ice shells. These ice shells are tens of kilometers in thickness. And one key example is Europa, the moon of Jupiter. And if you look at this, now we don't know exact thickness, so we think that could be anywhere from 10 to 30 kilometers of ice. But under that ice, there's a liquid ocean. That ocean is bigger than our ocean here on Earth. So that's how much water, liquid water, that could be out there. Here's the challenge for you. How are you going to get through 30 kilometers of ice? How are you going to get the energy to go through that? How are you going to communicate to get out of there? These are the problems. They're very tough problems. It will take generations and many, many minds. And you can be part of that journey. You can be part of thinking about what are the new clever ideas we haven't thought of today to explore these planetary bodies. Another example of this is Enceladus. So Enceladus, actually, we've taken this picture. Remember I told you about the Cassini mission. And you can see these things are coming from the surface. And these are very, very long here. And these are plumes of water ice that are coming out of this south pole of Enceladus. This is very interesting. So when we look where this is coming from, we see these stripes here. These are called tiger stripes. And if you look at a cross-section of that, that's what it looks like. Now, of course, here is exaggerated. It's not as steep here. But the stuff is coming out from some depression, some low point here in the middle. Okay? And this is what it looks like in 3D. So the stuff is coming out of this. Now, we don't know if it's coming from a point or there's a curtain of the stuff coming out. But we know it's coming out, right? And so one of the interesting things, can we go visit and can we take that water ice and try to understand if there's any organics, and organics are an indication of what could be there from a habitability standpoint. Okay, so these are examples, and I just picked a few examples because I could give a whole lecture about this, of what motivates us to think about ways to explore space. Now let me take you next to say, how do we explore space and what kind of systems do we use? So this is an example, let me see here. Oh. So this is an example of a rover here that was actually developed back in the 1960s. And people wanted to explore the moon. And you can see this is actually quite capable of going over this really rocky terrain. This was developed by JPL and General Motors. And the other one is another big version of it called the Blue Rover in 1986. Now, one of the difficulties about these two rovers is that it's very difficult to turn them. They're great going over rocks, but they're really terrible at turning. So people developed different versions of these. So back then, people developed very big, large rovers. Eventually, what we put on Mars was a very small rover here called Rocky 4. Actually, it was Sojourner, which was designed right after Rocky 4. So this was the prototype before we developed the system. But then later on, we developed this class of rovers, which were the precursors to what some of you may have heard of the Spirit and Opportunity, the Mars exploration rovers. So these were the prototypes that we were developing the research program at JPL before we actually developed the flight rovers. But the rovers are not the only type of explorers that we build. We also build, aerobots. Aerobots are very good for exploring areas where there's a thick atmosphere. Place where there's a thick atmosphere is Titan. And that's one place where we actually go ahead and use aerobots. And there's going to be a mission in the future called Dragonfly that will explore using some kind of a drone, a large drone that's powered with a reactive nuclear source. So this is the family of rovers that JPL has developed, starting with Sojourner. And that's when I came to JPL right here. And then working on the Mars Exploration Rover, Curiosity, and more recently, Perseverance. And these are almost siblings, except that Perseverance has a very sophisticated system to collect the samples for eventual and potential bringing back to Earth. But that's not all what we do, right? So these are the ones that you see in the news. There's a whole bunch of other ones that we do that you can search for that are ideas to seed the future exploration missions. So one concept is called athlete, and this is, it stands for all-terrain hex-limbed explorer, and it has 6 legs, and each leg has 7 degrees of freedom. So you can use these limbs as legs or arms to put tools and deploy instruments. Another concept, which is called Axel, it's an extreme terrain rover. So the idea of this is like a 4-wheeled rover that can send part of the rover over the cliff. And we'll come back to this later in my talk. Another one similar to Athlete is called Robosimian, which instead of 6 legs, it has 4 legs, but it can also do different maneuvers. And this was actually tested in the glaciers in Alaska and other places on Earth. And more recently, we are working on a snake robot, and that actually conceived to go into this vents of Enceladus. Remember, I told you about the icy world where the plumes are shooting up. So this is designed actually to go through these vents and explore there. Now, all these I'm showing you are concepts, and eventually, not all the concepts make it to flight, but some of them do. And one example is this Axel rover. So this is a lunar version, so we developed the concept to explore the moon. And we developed a system that's a very simple rover, actually. Sometimes it doesn't have to be too complicated. Has 2 wheels, and it has a bunch of instruments on it. And it has this boom, and it has the cameras here. And the key idea of this is that you can actually go down very steep slopes. And you can also use these big wheels to overcome the big rocks. And because it's simple and it's designed to be symmetric, if you flip it upside down, it doesn't matter. It's the same thing. You just turn the motors the other way. And you have very few motors, because motors, you know, the higher number of motors could be more challenging because they take a lot of energy, and you also have to keep them cool. And then you put instruments on them. And you can see here, so for those of you who are familiar with manipulation, if you remember, on a robotic arm, sometimes you put a turret, which is like a disc with a lot of instruments on it. So this has the disc inside the wheel, and then you can put as many instruments as you can put 3 to 4 instruments on each side. So you can have a lot of instruments on this simple rover without having a separate robotic arm. And you can point the instruments, and I'll show you that in a video. And you have a very good ratio of how much mass you have for the instruments versus how much mass you have for the robotic system. So we engineers love the robotic parts. But the scientist says, no, I want more room for my instruments. Because what's important is not the robot, it's to get the instruments to the place where we need to measure. So what happens, if you give them more volume and more mass, they love it, because they can put more instruments. And ultimately, we go there to measure, not just to have a robot drive around. That's not important. What's important is to take the instrument and put it where it's difficult to put. So think of the best way to think about it is like a yo-yo. It's a very simple idea. You go up and down. You don't need a surface. So this robot is what we call the yo-yo bot. So here's an example of how this works. So you can see you can move each wheel, and these instruments don't move, and you can move the boom. And then you have these instruments come out from the wheel. And then you can control the pointing of these instruments. And you'll see that in the video coming next. So I'll give you a look on the inside. What does this look on the inside? So on the inside, there are 4 motors. Each motor drives each wheel. And there are 2 motors that drive the middle section. So the middle section has 2 parts. One part is that boom, and the other part is a spool. And the tether comes through the spool, and there has to be some slip rings, like you have in your brushed motors. And then we can connect the electrical lines from the tether to the rest of the system. So why do we have a tether? A tether is very important because it supports the robot. But it also, inside that tether, there are wires. And we use the wires to provide power and to do communication. And then we have the instruments that are inside these wheel wells. Okay, so one of the things, so why did we need such a robot? So this robot was invented before we discovered these things on the moon. So this is a pit. That's actually a picture of the moon. And when we saw this is really intriguing. What's going on? So we took another picture, and we found, oh, wow, look at this. There's a hole on the moon. Why is this important? Because look, you can see these layers. These layers are about 70 meters tall. This means that we can go back, and if we can access these layers and we can put instruments, we can understand how the moon's secondary crust, how the moon's surface is formed. What is it made of? That tells us how the moon was formed. If we wanted to drill such a hole on the moon, it's going to take a big drill. So somehow this happened, and this is called a skylight, where the surface collapsed and it created this hole. So that's a natural hole for us. So the scientists were very excited when they learned about Axel and said, we want to take Axel and we want to land next to this big hole and then drive off the lander, rappel down, and take the measurements. Because that's what the scientists want, measurements on the wall. So this mission concept, which was led by Dr. Laura Kerber at JPL, was called Moondiver. And that's to understand how the moon was formed and how these lava layers were placed. And we can do that through the robotic system. So let's look at how Axel works. So this is another version of Axel we call dual Axel. And the idea of it is that you drive around until you get to the interesting area where you need to send the robot down, and this robot comes down with a tether. And like I told you, we can orient these instruments and deploy them to take measurements. And then after it comes back, the tether helps dock the system. It goes off and drives somewhere else. Now, even though this is a simple robot, it can actually drive over some pretty gnarly terrain. This is very difficult with a lot of boulders. And as you can see here, it's driving up and down that terrain. Now, actually, the steeper the terrain is, the easier it is. And you can see here, this robot's coming down this very steep cliff, just like that moon diver mission concept that I told you about. So this is the kind of field experiments we go out and do testing, because even though it may work in the lab, you put it on the field, it doesn't work all the time. Most of the time it doesn't work, so you have to figure out what's wrong and fix it. Okay, now, so I told you about a bunch of wheeled robots and a bunch of legged robots. Sometimes what we do is we have to look where are we going, and if that, and how can we make best use of the environment. So this is an example. If you want to go to an asteroid, and this is a 3D model of 67P, what we want to do is be able, how do you explore this? This is really difficult to drive around. And look what happens. If you put a rover like the Mars rover on this small body, look what happens. There is very little gravity on this. And as you drive, what's going to happen is you're going to end up flipping upside down, because it is maybe 1/1000th, 1/10,000th of Earth's gravity. So what do? Well, if there's such low gravity, why don't we build this different type of robot, something like this? That's a hopping, tumbling robot we call Hedgehog. And we put, the way it works is there are 3 flywheels, and when we can apply a brake on them, and this is on Earth gravity, so you can see it's spinning fast, you apply the brake and you move. Now what we did is we took it into a parabolic flight. This simulates asteroid gravity, and then we built versions of this here on Earth. And here I am in the zero flight, and we're trying to fly this robot, and then by spinning these wheels and braking them, you can take off. And what we do is we study, how does this robot take off? How does the robot interact with that surface? The surface you saw in the video was actually a simulant of that asteroid. So we have scientists who know what these things are made of. They prepare for us equivalent material. We take it to this airplane, and that airplane actually drops itself and free falls for 20 seconds, and that's when we do our experiment. So here's another example where this airplane is free falling, and when we spin, we're pretty much kicking up all this simulant in that enclosed chamber. So this is just another example of how we come up. We have to think of ideas that we can come up with to solve some of these challenging problems of exploring these planetary bodies. So, and here, let me just play this one here. You can see, oops. Yeah.
Two Hedgehog prototypes on a zero-G aircraft.
So this is another close-up where this is actually the asteroid simulant, and this is a close-up where you can see how, and we actually take these, high-speed videos so we can study the interaction of the platform with the terrain. So now this is, so I told you a lot about mobility and different types of explorers, different types of robots to go out there and explore different moons and different bodies. Now I'm going to switch to talk about the intelligence on these robots and how and why we want to make them more autonomous. So let's try to understand, what does an autonomous system mean? First of all, there's a NASA definition that says autonomy is the ability of a system to achieve goals while operating independently of external control. So that's a very short sentence, but that has a lot in it. So let's try to unpack this. So there's a system here that we want to think about, and that system is somewhere out in the solar system, and it's doing some control, meaning it's doing some kind of a closed loop function. And there's some kind of boundary between it and external control. Now, the external control here could be people on the ground trying to control the system. And what happens, people on the ground send commands to that system, and that system sends data back to Earth. Now, an example of this is, as I mentioned, a robotic spacecraft, and here are the ground team on the ground, right? That's one example, but there's other examples of this that doesn't involve the ground system. But the idea is autonomy is a relative thing. You want this to be independent of this. So you have to say, what is this and what is this, and that you're independent of. Okay. So now, when we build a system, and think of this as a spacecraft, we want to build a system that can allow the spacecraft to think on its own. So there's part of the system that's here in beige, we call the system that's going to be reasoned about. That has a whole bunch of subsystems and a whole bunch of states. And there's another part of the system, which we call the reasoning system, that's a higher level system that's going to interact with the system to be able to make decisions. And I'm going to get into this. So and what we do is we study each one of these subsystems and what is the relationship between all these subsystems. That's really important. Now, sometimes you learn that all the things that you learn in school regarding the mathematics that connects different parts of the physics of the system, and you can capture them using classical techniques. And these are very important for what we do in space. Now, there's a lot of interest now in also modeling this, not only with classical physics-based models, but with data-driven techniques like what you do in deep learning, right? So these are two different approaches of how you can model these relationships. One of the key challenges we have in space, we don't have a lot of data. We go somewhere we've never been before. So we can train something here on Earth, and it could be the wrong thing. But it doesn't mean that we can't use machine learning. Actually, we can in some instances where we have a lot of data, or where we can generate data artificially and have some confidence in training on artificial data and some data that we have from space. But also where you use this in the system that governs how well you can use it. So let's look a little bit more detail about what the reasoning system and the system reasoned about encompasses. So at the highest level, we have four parts of the system. We have what we call the execution, and that's the highest level of the system. Think about an orchestra, and you have a conductor, right? And the conductor just tells every musician so that everybody stays in sync. That's exactly what this executive does at the top level. But we have to also worry about multiple things. We have to worry about the system, the data we collect, and the health. Health is extremely important. Most people don't pay attention to it because here on Earth you can always go fix a robot. We can't do that in space. So we have to be careful to make sure that the system understands the health of every part of the system. And we're collecting a lot of data, and sometimes our storage fills up or our memory fills up, and we have to figure out ways to manage that storage. And then we have to make sure that we command the rest of the system so it can do the right thing in the right environment. Now, the system that's reasoned about has many different aspects of it. I talked a lot about mobility before, but there's a whole bunch of other areas that are equally important. Communication. If you can't communicate with the spacecraft, it's pretty much gone. No, it can collect the greatest information. You're not going to get back to Earth, then we lost it. Thermal. Space is extremely difficult. It's very, very hot. It can get very, very cold. I mean, even on the worst hot day or the worst place on Earth where it's really hot, it's pretty mild compared to space. Just on the moon, imagine, during the sunlight, it can get up to 127 degrees Celsius. And at night, maybe minus 180 degrees Celsius. That's what we have to design for when we do spacecraft for space. Power. Not a lot of power out there. So you have two options. Solar. You can bring your solar panels. They don't work very well when you're very far from Earth, from the sun. But then also you have nuclear sources like radioactive thermal generators. They give you constant power. It's not a whole lot. It's like a couple of 100 watts at best. So it's not a whole lot of power. Then you have to figure out how to get to your places, to your destination, which is how do you navigate among the planets, and how do you control your attitude, which is your orientation. And of course, what's really important, the instruments, to get these instruments to where we want to place them. Now, when you look at it, what's really important in autonomy is to think of two things. Think of a timeline, right? And we are here in the now. And then control and estimation is a way to look at the data from where we are today now and look in the past and estimate what information we have and try to control it. And that's a loop that a lot of you are very familiar with. Now, people in the computer science also look at planning and the future, right? And so there's another loop that's equally important is I want to be able to predict what's going to happen and plan. And that's another loop that's going on when we look into the future. So autonomy is about balancing this and having them work together so you can do the right thing at the right time. But sometimes we don't separate the estimation and control. Sometimes, actually no, the estimation prediction. Sometimes they could be really tightly one together. Okay, so I know this is a very busy chart, so I'm just going to go through it briefly to give you an idea of what goes on in autonomous systems. So at the highest level, we talked about the reasoning system. As I mentioned, the conductor of the orchestra, the executive. And it actually builds two things. You have to build an understanding of the world around you, but also an understanding of the spacecraft. And then we have something called co-estimation, and I'll come back and explain what this is. Before we fly a spacecraft, we know something about the world we're going to visit, and we know something about the spacecraft. I mean, after all, we designed the spacecraft. So we have models of the spacecraft, and sometimes we have models of the world. Examples of models of the world, we know where the stars are in the sky. We know how the planets move. All that information we can put on board. Now, in terms of the system that's going to be reasoned about, there are, I mentioned each one of these domains. So remember the thermal system, the power system, the motion system, which has navigation and attitude control, the communication, and the instruments. Each one of these have their own predictors and estimators and planners. These have to interact with one another, and they have to interact with the reasoning system. That is how we are thinking about architecting autonomous systems. There's a lot of interaction that are going on. Today, all the stuff is happening on the ground with people, but in the future, we'd like to start making these more independent and be able to make their own decisions. That's not an easy problem. There's a lot of unexpected things that happen in space. So that's what we're studying today. Now, I did want to come back to this co-estimation, and I'll give you an example. Why do we need, what does that mean, and how is this different than these estimations here? Think about it the following way. Think about you have a spacecraft, right? And that spacecraft is flying in space. And think about your attitude system. So that attitude system uses gyroscopes to tell you how that spacecraft is oriented. But sometimes these things do fail. So what happens when you have a failed gyroscope? You may get the wrong attitude. Okay? However, this spacecraft has solar panels. And you know if the attitude of the spacecraft is wrong, you're going to get less sun on that solar panel, aren't you? That gives you evidence that something is not correct. If this information is different than what this information is, if they don't show that there's consistency, you know something is wrong. That's one way to say what's going on with my spacecraft. Okay? So this is an example of what co-estimation is. And there's a lot more connections to be made in the system. These are the models that we build. So it's a lot of models that we build to connect the different pieces. And it's not easy to do. And there's a lot of computation involved. So let me give you examples of what already has been flown in terms of autonomous system. So we do things like deep space navigation, and we've done that autonomously. We also do entry, descent, and landing, and you've seen the landings on Mars. We also do surface mobility autonomously, and we also do above surface mobility, like you see here in the example. This is actually a flight of the helicopter on Mars, and that has to happen autonomously. Okay, so I'm going to touch upon two examples. So I'll tell you a little bit about the story of landing autonomously on Mars. So in 2003, we developed these Mars exploration rovers. And one of the capabilities that we put on the landing system, we put a camera. And the reason why we put a downward-facing camera, because we were worried that the winds are going to move the spacecraft too much, that it will have too much horizontal velocity. Why? Well, the spacecraft and the rover land on a parachute. And when you have a parachute, the winds could be trouble. Now, later on, in 2011, we developed a more sophisticated closed-loop guidance system and navigation for landing on Mars. But more recently, we also developed a system that uses something called terrain relative navigation. So here's how we land on Mars. We come into the atmosphere of Mars, and Mars's atmosphere is very thin, right? Less than 1% of Earth's atmosphere. And then, after we slow down by having the spacecraft and the heat shield slow us down because of the atmosphere, we remove the heat shield and we deploy the parachute. And then what we do is we look at the surface, and we look at features on the surface. And as we fly, because we have a map of Mars before, we match these features to the map before, and that will tell us how this is flying on the surface. And it will help us go to a safe landing site. If you go online, so this is an actual picture of the rover filming its parachute as it's landing on Mars. And there's videos online some of you may have seen. So what we want to do in the future is we want to be able to pinpoint land. So right now we have what we call an uncertainty ellipse, meaning when we pick a location on Mars, how accurately can we hit that location? In 2003, the ellipse which we can draw on the surface is very large. This means 150 kilometers by 20 kilometers. This means that we have to find a 150 by 20 kilometer area that's not very dangerous, right? And over time, we brought that down to a much tighter ellipse. And in the future, we want to make it within hundreds of meters. So this is an example of the landing for the lost rover, Perseverance, right? And all the red is where you don't want to land, right? You don't want to land on the slope, you don't want to land in the crater, and all the blue stuff is good landing site. And this is the imagery from the spacecraft as it's coming down. And what it's doing, it's finding all these features on the surface, and it's matching them to what it knows from before. And we do that at multiple resolutions. And you can see how this is changing shape. That's because the rover and the camera is tilting as it's coming down. And as you can see here, with the latest autonomous landing, we were able to land in a very tight spot. So if this is the spot where we landed. This is called Jezero Crater. And you can see if we landed on this side here, there's mountains. This is pretty rough here in this area. If we landed here, it's also not very fun. And if we landed here, that's pretty rocky. So we landed in a very sweet spot. And we did land, among hazards, and we landed with less than 5 meters from the retargeting error that the spacecraft picked as safe landing. So this is an example of the capabilities that have recently been demonstrated as of a couple of years. Now, you know about the Mars helicopter. The Mars helicopter is about less than 2 kilograms. And it is actually, it was an experiment. We didn't know it was going to work. It was supposed to do 5 flights. It has done 10 times more than that, and it's still going. And it's been flying and giving us an overview picture of Mars. With that, more flying vehicles are going to be deployed, and we can see here there is work ongoing on trying to collect samples from Mars through the helicopter as a backup option. And also Titan, as I mentioned earlier, is going to be explored with a rotorcraft. And Titan has a very thick atmosphere, so flying is a really good way to explore Titan. And the last one I want to talk about is surface mobility. So this is an area I work in. And this is actually footage of the rover driving on Mars. And as you can see here, there's rocks that you don't want to drive over, and the rover makes its way. And over time, we were able to increase the distance and the speed at which we are driving autonomously on Mars. So today, we have driven up to several hundred meters without anybody talking to the rover. So I think the record is somewhere on the order of 700 meters. So this is, okay. So this is actually what the rover sees, and it has stereo cameras, and the stereo camera built a map of what the rover sees, and these black lines are the possible paths the rover could take, and then it picks the white path to take, and these are the hazards that it sees through its cameras. So to put it in a more extreme environment, this is early research that led to the development of the navigation you see on Mars, which is a rover that's driving continuously, and we put a lot of rocks here, and it's trying to make its way to an area here, and it tries to get into this area here, and it realizes it's pretty rocky, I need to get out another way, so it replans its path, tries to make through here. Oh, that's too rocky still. Okay, backs up, figures out, gets around the rock, and then figure out its way to make to where we told it to go. So all this decision making, all the sensing and planning and estimation is happening on board the rover. So what's under the hood and when we do these things? Well, for those of you who work in autonomy, there's a three-block loop, which is the perceive, decide, act. And what we do for sensing, we do a lot of stereo vision. We generate what we call a point cloud. And then we generate the grid maps, and we use visual odometry. And I'll talk a little bit more about that. And then we have mechanical sensing. We sense the mechanism, and we have gyroscopic sensing to tell us how we're moving. We take all this information, we analyze the hazards, we come up with a certain cost of how difficult it is to traverse this terrain. We also sometimes tell it to stay out of certain regions because we know from Earth they're pretty dangerous regions. That gives us a global cost. We combine these two and then we make a decision. So this is a very high-level overview of what happens under the hood. So let's look a little bit closer. So this is an example of what the rover sees. And you can see every time it sees these, because of the geometry of the stereo camera, you see a wedge that looks like this. And as you can, the bright green is something we see closer, so we have high confidence. And as you go further out, the uncertainty in what you see gets worse, and that's why it fades out as the lighter green here. And then when it assesses its hazards, it marks these as the red terrains, and the yellow is somewhere in between. And then, and then it overlays a bunch of possible ways to go, and it calculates the cost of what it would take to traverse this path versus this path, and it picks up the lowest cost, and it goes. So we made that a little bit more sophisticated in the latest rover, where instead of just evaluating one arc, now we're evaluating two arcs, and we're exploring a better tree. And there's another thing we want to do is make sure we want to go to the goal, so we don't want to deviate too far, and we don't want to wander off the path. But also to check, we have to really check when we drive over this terrain, we have to make sure that the underbelly of the rover doesn't hit the rock. So we check and make sure that we have enough clearance. And this is a little bit complicated, and the reason it's complicated is because the rover mechanism here is a fairly complicated system. So as you can see in this video, it plays, or maybe not. Yeah, okay. Yeah, let me, oh, here. Yeah. Oh. Uh-oh. Can I, yeah, sorry. I don't know what I did here, so. Yeah, let's go back in. Okay, let me see. Let me, I can skip this one here, okay? Yeah, go ahead. Okay. Okay. Oh. Oh. Okay, here we go. Okay, so this is another video. So I want to go back to that rover with the extreme terrain and show you this video. So remember I talked to you about these recurring slope lineae, and these are where we thought there could be water. So this is a desert out in California called the Mojave Desert. And we did an experiment where we did a field test, and we took the rover out, and we started driving it in this environment to try to see how the rover does in the real world. So we drove it about 150-meter distance. And you can see here, this is a newer version of what you saw earlier. And this is a sped up video. And you can see this four-wheeled rover driving, making its way uphill. And it's turning and trying to go over the rocks and so forth. So it's making its way through this rock field. And then it goes ahead and positions itself where the front wheel, so now it does this called sit maneuver. And the front wheel part of the rover separates. And now this goes over the berm, and it's going to go down this slope. And that slope is about 30 degrees, which is pretty steep for the rovers. And then you can see here, it goes in and tries to collect some measurements. Now, one of the things that the measurements we're trying to do, if we're trying to explore water, we want to have a water measurement. So you can see the slope is about 30 degrees. And then when it gets to the point where it wants to take the measurement, it orients the instrument and gets ready to deploy it. And it deploys the instrument, and that's a spectrometer And that tells us a signature of water. So when we see certain spectroscopy, then we know that this is actually a wet patch. And so we had the scientists go in and wet the patch, and we confirmed that we actually detect the 1.4 and 1.9 micron water bands. And then it goes on, and it continues to explore. And it does another instrument. This is a dielectric probe, where it actually goes into the ground, and it looks whether it's wet or dry. And then the rest of it, what you see here now, is done autonomously. So that's what the rover is seeing. And it's planning and figuring out what the terrain looks like. And it's doing some planning while it's on the tether. So that's an interesting planning problem, which is called tether motion planning. And it sees this rock, and it sees this other rock, and it tries to weave a path between the two rocks. It has to worry about how the tether is laid out and how it anchors around the different rocks. And that's how this rover makes its way through some of this difficult terrain with the aid of the tether. And under the hood, there's this whole system, and there's a publication on this that I can refer to if you're interested, of how these different pieces work together to build that autonomous tethered-based navigation. And then as you can see here, when we come down, we have to worry about these anchor points, because if there's a big boulder or rock, then the tether wraps around the rock, and so we have to worry about anchoring from here, not from the top anchor. Okay? And we studied this by looking at, this is a lunar crater, and so if we come down this crater, which is 20 kilometers, then what would it look like, and can we do that with a tethered system? And there's also a number of publications on that I can refer you to. Here's a summary of what the rover is doing. The white stuff is done autonomously, and the black stuff is when we intervene and help the rover. And you can see this is a pretty difficult terrain that the rover is making its way down. So I want to wrap up with two things. So JPL has an autonomy center, and basically what we do in the autonomy center is we really try to figure out how we're going to make our spacecraft more autonomous. Even though I talked to you about autonomous systems, the spacecraft today are largely operated with a large ground operations team. So one of the things we did and published is a document about how do you architect autonomous systems. So people are interested, get in touch with me, and I'm happy to give you a link, or you can just take a picture, and then you can search that up. There's another center of autonomy that came up, which is at Caltech, called CAST. And Caltech is looking at developing technologies for explorers and guardians, transformers, transporters, and partners. These are robotic systems that are going to be autonomous, that not only work for space exploration, which they participate in, but also can help by doing things like flying ambulances, where they're flying autonomously with just the patient and without anybody flying this helicopter or drone. And they're looking at a whole bunch of new concepts and groundbreaking research and advancing capabilities. Now, so let me summarize. What I told you about is the stuff that we explore in space is very challenging, and the places we go are very hard. And sometimes today's solutions are not the way to explore in the future. And that will involve all of you is, how do we overcome these challenges of exploring these more challenging environments? And we have to worry not just about the robotic aspects, but about all these other aspects like thermal and power and communication. So it's all disciplines of engineering become critical. When we touch these surfaces, so it's easy when we're flying, it's never easy, but it's easier when we're flying in space, very hard when we get down to the surfaces or go inside these surfaces. And autonomy is going to play a critical role in the future for allowing us to explore more effectively when the spacecraft is able to handle these more challenging environments. And with that, I wrap up my talk. I do want to dedicate this talk to my former professor and advisor, Professor Michael Stanizik, who passed away recently, and that's how Professor Gonzalez Galvan and myself got reconnected after many years. And I do want to thank and acknowledge the contributions of the many for which I shared the work that they've done. And with that, let me end, and I'm happy to take any questions. Thank you for your attention.
¿Preguntas? Empezamos aquí con Samantha, allá y aquí.
Yeah. Go ahead.
Thank you.
Yeah.
Hi, first
Hi.
of all. What were the biggest technical challenges on making Ingeniería? Oh, sorry. What were the biggest technical challenges on making Ingeniería fly with almost any atmosphere on Mars?
Yeah. So it's a great question. Thank you for your question. So Mars has a very, very thin atmosphere. It's less than 1%, 0.6% of Earth's atmosphere. So one of the things that was really important is to keep the mass down, because as it gets heavier, you have a challenge, because how are you going to generate power? And you have a very small solar panel, so you're limited in power. So one of the key things was to engineer it to really make it very light. That's one thing. The other thing is that you not only have to worry about the flying, but you have to worry about making sure it stays at the right temperature ranges. Because if it's too cold or too hot, you have to heat up sometimes, you have to cool. So thermal management. And then you have to make sure that you really land safely, because as soon as you topple, then it ends the mission. And you have to stay within range of the rover. So I would say the systems engineering of it was very, very challenging. Once the concept was proven, because we have these thermal chambers and we can lower the atmosphere, then it was all the system engineering challenges, which were, quite hard, but it was a great team who pulled this together. Thank you. And by the way,
amazing.
I'm happy
Thank
to
you.
stick around for a while. I know some people may have classes, so feel free if you have to go. But I'm happy to stick around for as long as you have questions. Yeah. You want a microphone? Yeah.
I'm really glad to have you here, but this is not necessarily from topic, but I really want to know how, as an average Mexican student, how to get to work in NASA.
Okay, so one of the key things is to really master an understanding of the things you learn. And believe me, you'll be surprised how much of what you learn becomes really important for space. So when I was a graduate student, an undergrad, I was more into robotics and electronics, and I wasn't very interested in thermodynamics, but I had to take thermodynamics. In my job today, thermodynamics is so important because we have big thermal challenges, and I never thought I would need it. You'll be surprised how many things you may think, oh, why am I doing this? Becomes very important. So my advice is learn the stuff to not do well on the test. Learn it to understand it really well. Once you understand it really well, things will fall in place. You'll do well on the test. It's very hard to remember everything. But if you put the time in and you really give it, because it takes time to learn all these. There's so much to learn. It'll really become very important. So, learn the fundamentals, practice them, do the projects, develop deep understanding, and then you have to really apply, and it's tough. It's a lot of competition, but I think stay determined, and I think there's opportunity out there, and you never know how things work out. Sometimes they do in the least way you expect them to.
Well, thanks.
Sure. Yeah, over there.
Sir, in your experience, which is the best or the highest goal you want to achieve? Like, in your whole experience, right now, which idea you want to make it the top goal?
Yeah, so to me, so everybody will have to set their own goals, and figuring out what your goals are is always a challenge, right? To me, at this point in my career, it's important to work on problems that are worth solving and that add even a small value. And so I'm a little bit careful of what I work on and how I spend my time, because I'm more than halfway through my career, so I want to make sure I focus on, and there's a lot of challenges. There's tremendous amount of challenges in space exploration. So you pick a part of the problem and then you dedicate yourself to it. But ultimately what we do is the work of many colleagues. And I think being in an environment where you can brainstorming is really important. And sometimes somebody may propose an idea, everybody will laugh. That may be the best idea that proposed. Initially everybody's skeptical. A lot of times this happens. Happened to me. One time I was laughed out of a room about an idea. But then because people didn't think about it. So don't be afraid to put yourself out there. You know, throw your ideas. Sometimes they're not, you know, the best ideas, but it's okay. Sometimes they are the dark sheep that changes things. So sometimes it could be the best idea, but just people haven't come around to doing it.
Good afternoon.
Yeah.
I'm very keen on autonomous systems, and I'm a mechatronic engineer student, so what program do you recommend me to take a master's degree in Caltech?
Yeah, so I think, so there are 2 departments in Caltech that work in the area of autonomous systems, actually 3. There is the controls and electrical engineering department. There's mechanical engineering, and there's also the computational sciences department. It depends on what's aligned more with your interests. There's also, I mentioned CAST, and CAST is a center that has all these different departments working together on projects. So a lot of times in the graduate school, the projects become very cross-disciplinary. Of course, they have GALCIT, which is the aerospace department, and that they do a lot of autonomous systems as well. So there's actually, you know, multiple departments. I think the key thing is to say if you want to go into aeronautics or aerospace, then I would say the aerospace department, aeronautics. If you want to, you know, more on the robotic, physical, then maybe mechanical engineering, thermal. If you want to do more on the control side, then it may be the other departments. Yeah.
I wanted to ask which are the biggest areas of opportunity, like in short term and in long term, for undergraduate students like us, and also like coming from Mexico, because we don't have like the same like areas as international students. Yeah.
So let me say one thing. So sometimes people think when you have fewer resources, then it's more challenging, and it is in some way. But look at it as an opportunity. See, I grew up in a very humble environment, very limited resources, but what that does, it drives creativity. If you have to solve problems with very little, you're going to become a very good engineer. And when you have too many things, and you know, your problem becomes easier, so you don't think hard. This is the time to think really hard. This is the time to solve really tough problems. It's okay to struggle. It's okay to fail. Let things break. You will learn tremendous amount. And that's what makes good engineers. Because the problems we solve never been solved before, and we fail sometimes. But it is the thinking, and anybody can think. You have a brain, and you have the books, and you have the resources, so you can do wonderful things. So I think, you know, it's within. You got to look within. You got to be determined. Say, this is what I want, and you fight for it, and things happen. And you have to have luck too. I mean, it doesn't happen. It's a lot of ingredients that have to line up, but sometimes you'll end up doing things that are very interesting. You never have thought about them. I never thought I'll end up at NASA. And the first time I applied, I didn't get in. But you got to, you know, things work in very different ways, and you have to stay focused, stay, you know, committed to what you want to do. Yeah. Oh, okay.
Well, following with the previous question, I was wondering what us as engineering undergraduates could do in order, if we want to apply for an internship, or if it's even possible.
Yeah. So we're going to tackle that question in a little bit more detail. But so for international students, it's very difficult because the resources are all for national students. Now, if you get sponsorships from Mexico, from your university, from your government, then that opens up more opportunities, because you're just looking for the experience, but you're not looking for the resources. Believe it or not, the resources are limited everywhere. And so I think that's an important part, you know, is to identify means to allow you to do the, you know, to have funding sources that allow you to get these opportunities if you were to get an internship. Yeah, and we'll talk some more about that later on in the evening, if you're going to be there.
Hello, I have one question. Have you worked with the team, SpaceX team? And if so, who was your experience with them?
So this is a question, have you worked with the SpaceX team?
Yes.
Yeah, so JPL does work with SpaceX. I have not worked with SpaceX, but there are people at JPL who have worked with SpaceX, and we have, but I can't comment any further on that because I have not had that experience. Yeah.
Hello, good afternoon.
Yeah, good
I would
afternoon.
like to ask two questions.
Yeah.
They're more technical questions. When you do the test for the rovers, you always shown us many tests that you do in the planetary environment,
Yeah.
but you also need to do the tests at the moment of the launch environment, for the vibrations or so.
Yeah. So there's different tests that we have to go through. So when we develop a new concept for a robot, we have to go and take it out to the field. And what we have to do is we have to test it in what we call irrelevant environments. So we have to answer the question is when we go out to this particular area, why is that particular site relevant to the space environment? So different sites have different relevance. That tests the robotic system. When we build the spacecraft, that's a different set of tests we have to go through, which we do the verification and validation. So that's when we actually take those systems and then run them through vibration testing and thermal testing for launch. There's a difference between what I showed you as a prototype, which will not have all the engineering that's needed to fly, and what we end up doing for flight system. Because a research project doesn't have a lot of money, but you have to demonstrate the idea. If the idea is very promising, and if this becomes a flight project, then there is a big program to actually do all the development and testing in the chambers, the thermal vacuum chambers, in the vibration testing, so we can fly them, radiation testing, etc.
Okay, thank you. So the other question I would like to ask you is that when you shown us the onboard systems, you told us that you can use one way to solve a problem, and if that does not work, then you go to another path to achieve to resolve the problem.
Mm-hmm.
But are you allowed, when you design these rovers, to have redundancy in systems?
To have, I'm sorry, what was the lot? To have what?
Yes, if you are allowed to have redundancy in systems, meaning that if a system does not work very well, you could count with another one with the same properties.
That's a very good question. So it's actually not allowed. Sometimes we're required. So in our missions, there are multiple classes of missions. So we have class D, C, B, and A. Class A is what we do when there's humans, astronauts. JPL doesn't do a lot of class A work. That means when you have a human working with a robotic system, it has to be redundant in different ways. Class B means it's a very expensive mission, so it has to have redundancy in computing, in anything that could fail. So it has to have some redundancy. Redundancy could be in two forms. I call it, you have two processors, you have two camera systems, etc. But it could also be functional redundancy, meaning that if this fails, I can use something else instead. It's not identical, but it does give the same functionality. So the Class B missions, which are the big projects like Cassini and the ones like Voyager, they have to have redundancy. Class C has less, and Class D is experiments. So when we put the CubeSat or the helicopter was Class D. So it didn't have to have the redundancy.
Okay, thank you very much.
Okay. That's a good question. Yeah. Okay. Oh. Okay.
Okay, so I have two questions. Is that right with you? Okay. So my first question is, when you're dealing with complexity, having so many parts, do you guys have a stopping point where you say this is too complex, and how do you avoid over-engineering your solutions?
Yeah, that's a very good question. So throughout the process, when we do, so there's also a difference between research and flight. So on the flight side, so let me answer this on the flight side. What we do is we have reviews, they're called preliminary design review, critical design review, and so forth. So things get reviewed all the time. And what we always do is we try to find what is the simplest solution that solves the problem. So if there is ways to really reduce complexity, we'll go after it. But sometimes what happens is that you have certain need. You have to have this measurement, this instrument, and that instrument has to go somewhere. And so sometimes that drives the complexity. Like if you want to collect a rock sample, that drives the complexity because you don't know how hard this rock is. You have to break it off. You have to collect it. You have to seal it. But it's important to collect the sample and bring it to Earth. So that's where the value is. So we look at many, many options. So what we do is we have something called a trait study. We look at what are all the ways we can solve this problem, what are the pros and cons of each, and then we pick what is the lowest risk and most effective solution to the problem.
Okay. And my second question is, from what I understand, these autonomous systems can be quite computationally complex.
Yes.
How do you guys deal or strike a balance between the power that you draw from the system and dealing with an environment where there's low power?
That's a very good question. So there's always tension among all the different subsystems, right? You make it smarter, it's going to draw more power, it's going to need more computing. Now you take power from doing other things. So it's a delicate balancing act. So one of the things that's great that's happening is the computational cost is going down in terms of power. And the availability of more advanced computing for space is happening. People are working on it. So that's helping on one side. But on the other side is you have to be really careful of how much computation you do, and is it absolutely necessary, and is there a simpler way to do the computing to get the answer? It's always a trade among the different, because limited resources, you have only limited power and you need them for different things. So that happens on every project. Every project tries to look at what is it that they absolutely have to have on that mission, and how do they balance it? So partly what we do sometimes is, like on the helicopter, right? You're going to fly, but you can only fly for a few minutes. So the other thing you can do is when you design the operations, how long do I fly? How long do I charge? How long do I use for computing? And how do I split my time to figure these things out? And that could happen. Sometimes we just have to wait. We just sit there and wait because we don't have enough power, or we need to warm up a little bit. So that happens. So there's another flexibility we have is designing what we call the con-ops, or the concept of operations.
Thank you.
Sure.
Let me read this question from the transmission that we have right now. They asked me to ask you, Issa, what is the good advice that you would have liked that will be given to you when you were a student or during the process as an engineer?
Yeah, that's a good question. So I would say, I wish I got the advice of the things that you think that you're going to need the least may end up being things that you're going to end up needing the most. Don't count something out. I mean, I look at the educational period as a really golden opportunity. It doesn't feel that way when you go through it, believe me. I didn't feel that way. We have lots of courses, lots of exams, a lot of pressure, and then you're trying to balance your academics with your social life, with your friends, your health and everything. But ultimately, at the end of the day, it's a really precious time to really do the deep thinking, the real hard work. And it gets harder later on because you don't have that time to concentrate. So I wish I paid more attention to the things I thought, I don't care about these. I think a lot of things become important. Even though, especially if you do business like space, you'll be surprised how many things come into play. So I wish I got that advice early on.
So, well, in your personal experience, how much is artificial intelligence used in JPL missions, and what are the challenges they face with in artificial intelligence implementations in robotics?
Yeah. So let me tackle. So there's more and more, we're doing more with artificial intelligence than we've done before. What we end up flying is still very conservative because, some of the things I showed you are very expensive, and they happen once every 20, 30 years. So they're very rare and very expensive. So people are very careful of what they try to do to make sure it succeeds. When we talk about artificial intelligence, sometimes people equate artificial intelligence with machine learning. There's other techniques in artificial intelligence that are not machine learning. planning and scheduling, there's certain navigation things I talked about. These are all, processing of imagery and assessing hazards and taking motion planning. All these things are part of what, consider AI, but they're not necessarily machine learning based methods. Now, even in machines, so I always say one thing. In space, because it's very difficult, you can only rely on one thing: physics. We know physics holds here on Earth and anywhere else in space. So if we understand the physics, and the more we understand it, that's the thing we can build a foundation on. Now, this doesn't mean that machine learning, deep learning is not important, actually very important. Sometimes where we actually have been able to use these very successfully and shown great results, let's say I'm trying to image match. I'm trying to match features. We've seen even better performance using machine learning for feature detection, feature matching than any of the classical techniques. But again, more and more machine learning is going to make its way, as long as we can figure out a way to make it reliable, even when we have the different data. So in this machine learning, you may be familiar, if you have auto distribution from your training, then it's unpredictable, right? And by definition, a lot of things we do in space are out of distribution because we've never been to them, especially when we go to a new place. So I think we have to be careful. So I think machine learning and our AI are going to continue to increase, especially when we talk about autonomous systems. So that's important for the future. But also understanding with anything you do, not only understand the capability, understand the limitations. To us, knowing the limitations is more important than knowing the capabilities. We need to understand how these things fail. And people sometimes don't, you got to look at those in great detail.
So what would be the next stage or the challenge to overcome so that we could go to the next step in space exploration as mankind?
As in general, as a next step?
Yeah.
Yeah, I think there is no one specific next step, depending on, so there's a process that the science community goes through. It's called the decadal survey. The decadal survey happens every 10 years. A lot of the scientists, in the country get together and discuss what are the important questions to answer from a scientific exploration. That drives what we do on the exploration side. So because they do that every 10 years, sometimes the priorities can shift depending on what we discover. So right now, there is a report, and you guys can all access it to see what are the important questions in terms of exploration. So one of the interesting questions, I talked about that lunar rover that has to drive 2,000 kilometers. That's one of the important questions that the science community said should happen within the next 10 years. The other one is the Uranus mission to go and explore that. So that's an important one. There's a few other ones that are also important in terms of visiting a centaur, which is a small body, and there's a couple of other ones as well. So and those things, sometimes several of them will happen. Sometimes in the next decade, there'll be a new set of priorities. Again, there's only limited money. You can't do all the missions. But they try to decide which ones are the most important to do based on the big science questions to answer.
And for you, which one's the most important?
Well, I work on, I work on different things. So I do work on the rover system that has to drive really fast on the moon. So that's one area I work on. But I also work on autonomous systems. So how do we access small bodies autonomously? I didn't show a video of that. I can show that later in the afternoon. But that's it's a very difficult problem because you're visiting a world that you have never seen and you don't know what it looks like. So I showed you the picture of the 67P, that big asteroid thing. It's something like that I've been also working on and very interested in.
I think it's maybe time to close, but Dr. Nesnas is going to be here for a few minutes more. If you want, you can ask him directly, if you want, or those who has still some questions. Dr. Nesnas brought some souvenirs for you guys, so please stay here for a little while and we will give it to you. And also, I would like to thank you, Issa, for your very nice presentation, all your experience that you have shared with us. I'm sure that our students will feel more motivated to study very hard, you know, and realize that all the courses that you take are important, because you don't know when are you going to need them, when are you going to use them. Yes? Oh, yes. Don't forget, I want to switch. No se les olvide la conferencia a las 5 de la tarde con oportunidades de interacción con la NASA y JPL, por favor, para que nos acompañen también aquí. I'm going to give Issa this paper of recognition and a souvenir too for you. Let me have it here. It says, la Universidad Autónoma de San Luis Potosí, a través de la Facultad de Ingeniería, otorga el presente reconocimiento a Issa A.d. Nesnas, Ph.D., por su valiosa participación como ponente de la conferencia Robotics and Autonomy Systems for Space. San Luis Potosí, 8 de septiembre de 2023. Atentamente, siempre autónoma por mi patria educaré, firmado por la dirección de la facultad. Issa, thank you, and yes. A small souvenir for you.
Thank you.
For the 100th anniversary of the autonomous, a different concept of autonomy, I will say. You know, it's not the same idea, autonomy. Thank you, Issa. Thank you. Así que los esperamos, por favor, a las 5 de la tarde. Por ahí, Rosma y la doctora Sandra les van a entregar alguno de estos souvenirs que el doctor Nesnas ha traído para todos ustedes. Muchísimas gracias y nos veremos por aquí un poquito más tarde.
Thank you all. Thank you.